Welcome! In this video, I am going to tell you about a simple mathematical game of Platonic solids. This is in fact a zero-player game, which means that you don't really get to play it. Instead, you only get to watch it as it plays out in front of you. Let me first start with the Platonic solids. Those are three-dimensional objects with identical regular polygonal faces, and at every vertex, the same number of faces meet. These solids have been known for a very long time, and you can find in one of Euclid's books the proof that there exist exactly 5 of them. There are the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. I should say that the work I am about to present in this video was published in the European Journal of Physics by my colleague R Low and myself. There is one more thing I need to tell you about Platonic solids. For each of them, it is possible to draw a sphere, known as the circumscribed sphere, passing through all the solid's vertices. But before I go on telling you about the game of Platonic solids in 3 dimensions, I suggest we look at the same game in 2 dimensions. Let us start with a square of length L0 equal 1. This square fits inside a circle for which the diameter is equal to the square root of 2. The rule of the game consists in choosing a random length smaller than the diameter. We will call this new length L1. We now have to build a new square of length L1. We can forget about the original square, and we are going to repeat every steps of this construction process. First, draw the circle associated to the new square, then measure its diameter, and select at random a length L2 smaller than the diameter. With this new length, we build a new square. The game is to iterate this construction process over and over, always building a new square out of the one we had just created. In this video, we can see the game playing out. What you observe here are the squares which are being generated by applying the rules I have previously mentioned. Eventually, the squares are getting too small, and therefore, so that they would not appear as a single point, I have tried to scale them up by multiplying by a factor as indicated next to each square. But as you can see, I am not doing this fast enough, and they still get extremely hard to see very quickly. Now that we have an idea of what is happening, a few questions come to mind. Knowing that the first square is of length L1, can we estimate the average length of the nth square? The key word here is average. Because the game involved a random choice, predicting the exact length of a square after a given number of iterations for one particular simulation is not possible. At best, what we can do is to find the probability to observe a square of a given length after n steps. This is what we call the probability distribution. But this is a little bit too technical for this video, and if you want to know what this distribution is, I would invite you to look at the paper I have mentioned. Now, the average length of a square after n iterations is something that is often written like this in the community of statistical physics. But if you have a background in mathematics, you may be more familiar with this notation here for the expectation value. Here is another question you may be interested in answering. Can we estimate the average area of the n square? This is something you will want to write like this or like that, depending on what is your favorite notation. Because one square is constructed from the previous one, we kind of expect that there must be a relation which relates the average length at step n to the average length at the previous step n-1. And with a little bit of work, we can show that this relation is simply ln equal 1 over the square root of 2 times ln-1. Along the same line, we can show that the average area L2 obeys a very similar law. Both equations are very easy to solve, and we show that both the average length and the average area are given by a constant to the power n. If we plot those two quantities as a function of n, one clearly sees that both functions are quickly approaching 0, which is consistent with the squares becoming smaller and smaller as seen in the simulation. We should note that if we square this first function here, we get this new curve, which as you can see is different from the green curve for the average area. This is a reminder of the fact that in general the square of the average is different from the average of the square. This is a well-known fact of statistics, which is used to define the standard deviation sigma, simply written as the square root of the difference between those two quantities. Let us now move from a two-dimensional space to a three-dimensional space. I will use the cube as an example, but you can play this game with any other Platonic solids. Starting with a cube of length 1, we draw its circumscribed sphere and measure its diameter. We then select a new length, smaller than the diameter, with which we are going to build a new cube. We have to repeat this process over and over. Just as before, the question we wish to answer is, knowing that the first cube is of length 1, can we estimate the average length of the nth cube? And just like before, we are also interested in the average surface area and the average volume. Therefore, we are going to focus on three quantities, the average of L, L2 and L3, which I could collapse in one notation, representing the average of L to the power k, k being any positive integer. Once again, we can show that this quantity at step n relates to the same quantity at step n-1, which leads us to conclude that the average of L to the power k after n steps is given by this function. Let us first set k equal 1. We see that the average of L is equal to the square root of 3 over 2 to the power n, which tends to 0 as n tends to infinity. If we now set k equal to 2, we see that the average of L to the power 2 is equal to 1 to the power n, which is always equal to 1. Since a cube has 6 faces, the average area of the cube generated after any arbitrary number of steps is equal to 6. Finally, let k equal 3, we see that the average of L to the power 3 is equal to 3 square root of 3 over 4 to the power n, which diverges as n tends to infinity. So we can conclude that as the number of iterations tends to infinity, the average length of the cube converges to 0, the average surface area remains constant, and the average volume diverges. Now, this may appear paradoxical, but the key word here is average. Of course, at no point do we have a very tiny cube with an infinite volume. Such apparent paradoxes are familiar in the field of stochastic processes, and you may have run into similar apparent paradoxes when studying a simple random walk. If you care to know what happens when one tries to play the same game with any other Platonic solids, or if you want to know what function describes the length distribution, I invite you to read our paper. I hope you enjoyed this video, and I will see you soon.